Well, good afternoon. I feel a little bit more organized than I did last week. I don't know why. I'm feeling better, though, in my hand, too, which is good news. It hurts. I can make it hurt, but I think I'm pushing the limit little by little back to reality is what I'm hoping for. So this week, we have the homework due. 3 of you have turned it in. 1 is probably going to have it in shortly. No rush, though. Just push it on Slack, and I'll know when you pushed it up there. And we have a new assignment set out there, number 2, which is out of chapter 2 in the book again. It continues on from where we left off, kind of meanders around on this time a lot with difference equations, and then the Fourier properties, frequency responses, taking advantage of the Fourier transform. So we're going to continue where we left off, and I'm going to try to be more linear tonight. I'm not going to try to jump around, because last week, admittedly, I was scattering because my brain was saying, oh, you got to have this, you got to have that, and oh, you got to learn how to use Python too. It's just kind of like whenever you do something new, you have to bite the bullet and say, I got to get, if you think of a curve, you're climbing a steep learning curve, and all of a sudden then you can climb up and start flattening out and feeling a little bit more at ease, which could be starting a new job, literally climbing a hill. I do a lot of cycling. This summer I was in Washington State. I probably mentioned that. I haven't put pictures up yet, but when you're on a long climb and the next bend you go around, the climb continues, and the next bend around that, it continues, you start to get a little bit daunted about, I'm never going to get a chance to catch my breath. I'm going to be grinding away. But once you get up on the flat spot, then you feel really good about it. And if you lose some elevation, it's okay. But in engineering, I don't worry about losing elevation, because you don't do that. You're always going to be learning, and you're always going to be getting more. And your brain doesn't get dumped out unless you have some bad accident or something, I suppose. But okay, so we could go look at the homework, but I'm not really going to look at that right now. I may look at that later. I did post things between last week and tonight about using types in Callisto, which is the package that lets you bring in sections of Jupyter notebooks. It works really, really well, but if your workflow is what it is, and I've looked at a couple of papers, just carry on using that. But if you want to tinker and see that might work in, my solutions are not written using Callisto and types, because I've had so many solutions written out over so many years. I use a different environment. I use an old Adobe product called FrameMaker, which I've been using for a long time, and I may try some problems in that, but I just got to be efficient about getting things out the door and moving on to the next thing. So what we're going to do now, we will end up over here in Jupyter, and I did push a new version. I didn't push it onto the website yet, but I took the old chapter 2 fall 2024 and I imported it into here yesterday, and I started making some changes and tweaking to it. So probably after tonight I will push this up onto the website. So what I'm talking about specifically is down in here. What I will be doing, I think I edited this already, but I don't think I had anything new in here yet, but this will, let's see, no, this one, yeah, this is the one I'm talking about. This notebook right now is from last fall on September 5th, but I will eventually, push just a slightly updated version that'll be reflective of anything we're doing in class. It'll be just a minor tweak, though. So that'll be out there. The solutions will go up later, too, for set number 1. They're already in my iCloud drive, along with your papers that are assembling there, so that I can pull them up in my tablet and grade them and that sort of thing. So I'm ready. I'm staging myself to get that going as well. I think a comment we had about getting documentation on scikit-dsp.com, remember we have a link over in the website, and that link is under course materials. I've got read the docs for scikit-dsp.com. So I will probably refer to this maybe tonight, or I'll just bring up the online help at the same time. But this has got everything in it, and the module you drill into mostly for us is going to be the SIG-SYS module. So Miles, what's a example of what you were wondering about? We'll just pull it up. What function?
Oh, what was the function you said? It was conv_sum.
Oh, okay. Convolution sum. Yeah, that's, so we'd go down here, and there's, there it is. And I'll be demoing that in a little bit here. And then explains the parameters, and then my co-developer has got at least one example in here. And you don't have to use all these arguments. So one of the things you should learn about Python is the idea of optional arguments. So this idea of setting what I call the extent is kind of confusing to me after I've written it so many years ago, and most of the time I don't even use it. So what you know, though, is if you see an equal sign next to some variable in the function prototype, you know that I don't have to supply it. If you don't supply that argument, it just goes to the default value, and that's a good way to code, right? Don't try to understand all the optional arguments, just let the defaults take place. And anything in the Python libraries are loaded with optional arguments. You don't have to use them, though. You can just fly without them, but you can drill in if you want to understand what some of the options are available. But you do need to supply these first four, and I'll leave that up for later. But now we're going to jump over and get back over to the notes again. This is kind of backing up a little bit for review. We were looking at discrete time systems, and we looked at the T operator, and you've been exposed to that a bunch in the homework problems, the idea that we have some operator transforming the input sequence to an output sequence. We looked at the moving average as an example, and then we talked about the causal moving average, which was what happens when we set M1 equal to 0, and this will be a very popular setting on this particular type of smoothing filter or averaging filter, where we just take the present value and take, in this case, 5 samples into the past, or 5 samples into the past in this picture, but then down here I did 5 past values and the present value. So then we were continuing more definitions, and this we went through last time. Are there any more questions on these? That's what I was doing just before we started class. Let's see. I'm trying to remember names now. So Lantau or Lantu? Lantu? That's what I was doing when you walked in. I was taking questions because I was using like an open time before class started. So we were looking at I guess, what to do if you have to prove something is stable and you don't know if it's linear and time invariant. Most of the homework problems, we use a theorem, which we'll be looking at here shortly, formally, but if you don't know that it's linear and time invariant, then you have to rely on the definitions, which are right in here, which you basically, for the bounded input, bounded output property, you just established that if the input's bounded, that means you can write up some Bx as the upper bound on the magnitude of the input. Then you have to be able to establish that the output magnitude is less than some By, which might be a function of Bx and some other variables in the system, to establish that it's bounded output. And I always point out this last bullet where it says if It might be easier to show that it's not bounded because you just have to find one situation where it blows up and then it breaks it. So then you know it's not a stable system anymore. There's also occasionally in some of this stuff, but we kind of get away from all this formality stuff after this first chapter, but things you might remember from taking calculus, you can do something called a proof by contradiction. Do you remember that? We're going to see that in a few moments here, actually, proof by contradiction. You assume something that's counter is true, like, oh, it must be possible to get this to work without this condition being true, and then you come up with a condition, a particular type of input, let's say, that makes it go unstable, and it's because you've done the flip of that condition and it makes it unstable. So you're just showing that it is a requirement, and that's proof by contradiction. So we went into the convolution sum, making the assumption that we have an LTI system. So this is like the big beginning point for what's going to be true essentially all the time unless stated otherwise, that we have a linear time invariant system. And we talk about the impulse response. So the LTI system just means two of those 6 or 5 properties are true, namely linearity is true and it's time invariant. Do we ever care about anything else? Yes, we do, but most of the time these two are held fixed. I think I mentioned that adaptive filters as an example of a system that is time varying, like if you have adaptive noise canceling headphones or something like that, that's what makes them what they are, right? You put them in and all of a sudden the sound just goes away. And if you haven't tried that, like going to a store or something and trying them out, they're pretty amazing. And they've been, I think, the first example of that type of time varying system for DSP audio, I think my understanding is like on the flight deck of an aircraft carrier. The people that are working out there are exposed to huge sound pressure levels and they need to be protected. So not only do they rely on the pressure of the ear cup, they rely on the anti-noise that can be generated by sensing the environment outside the ear cup and then sending that in to your ear. And when I say anti-noise, I mean out-of-phase sound waves that cancel the waves that are naturally trying to arrive at your ear. Now, I'm subject to talking all kinds of things because I've studied so many different things, but the automotive thing that's supposed to be out there in some of the high-end cars is noise canceling without wearing any ear cups, just being in a space where there's a zone where anti-noise is fairly effective. So if you stay in this certain zone, you're in like a quiet zone. But what do I know as a cyclist, and what do you know as maybe a runner or a hiker or a walker on public trails? If you can't hear what's going on around you, you could be bowled over by somebody and killed. So I prefer to, when I'm on public trails like that, I don't want to have sounds blocked. You got to be smart about things. But question?
Why is noise canceling time varying?
Because the property of the system is changing with time. You know, one moment it might look like this particular response for this type of stimulus, and then when the signal comes along differently, like when the outside stimulus, the noise you want to block, like the jet engines or whatever, when that's coming up or down, then the system will change its properties accordingly.
Okay.
But it could be an adaptive filter might be used to remove a jammer too, a jammer that's moving around in frequency, and then it would be following the jammer to make sure it's canceling that signal out. That's actually one of the projects that's up for this class, and it was used last year, but I'm not thinking of using it this year, but it is out there. You could look at it and see how that works. So we have, when we went through this, we already talked about this, we get this blue boxed equation, which just says that once we have an impulse response for a system, which is a particular characterization, and that characterization is when we fire a delta sequence into a at-rest system, it produces the impulse response, which I consider to be like the signature. It's the signature response of that system with the impulse. But control systems people like Dr. Trimboli or Dr. Plett, they might prefer step response, because control systems people like to think about step responses fairly often because they're talking about controlling something, and to them the step response might be the more important thing. Like if you're controlling the position of a rudder on a ship or something on an aircraft, you're going to give it a position change and you're just going to hold it steady, and you might want to know what sort of response you get. So a trivia question is, a delta function in the discrete time domain is very precise, like shown over here. I think about when I'm driving and I'm seeing potholes that I'm wanting to avoid, because once I drive and hit some really bad ones, I want to learn how to avoid them. What do you think a pothole looks like as a stimulus to your system, like your car suspension? Do you think it's kind of like a delta function in a mechanical sense? I do, actually. If you look at it sort of from a distance, it's like you come along, bam, then your car does what? It kind of oscillates or responds back again. So you can have a mechanical interpretation, and I think mechanical engineers like that. And electrical engineers maybe wish they could always do that, but I'm fine. I mean, I can just think about a mechanical system and say, that's an analogy, but we still have an electrical sense. So, I mean, to me, just tapping the desk like that, suddenly there's vibrations, and that would be the mechanical response of this material getting struck with a hammer or something. So now I'm going to walk through this example. Even though it was used a lot in doing homework problem number 1, I want to spend some time on the geometric series. The setup of this problem, though, was something I wanted you to study a lot. So I guess, did this problem help you get into problem number 1 on the homework? Okay. So you get the idea that if you have to do a convolution, you have the two waveforms, or two sequences, h of n and x of n. The roles could be reversed, but you go back up here and you say, okay, I can either use the first version or the second version, right? Either one works equivalently. For me, when I'm doing a problem, a homework problem like this, I generally prefer to make the flip signal, the n minus k waveform, be the one that's the easiest to visualize the flipping on. Does everybody agree? I mean, both should work, and if you really want to work yourself over time, just take any problem you've already done and do it the other orientation, and you'll get an exercise. You should be able to do both ways, but I personally say pick the way that's the most clear to make sure you're not going to make a mistake. Problem solving always has pitfalls, right? And what's one of the things you probably learned by now is that don't make the solution approach you choose to be the hardest one. That's just asking for trouble. But for me, I like to work in multiple ways, because as a professor, I've had to grade homework papers over many, many years where somebody picks this other method, and I've got to figure out if what they did actually works or not. And you've probably been in that situation before, where you look back and you say, if I would have chosen this approach, it probably would have been easier. I don't have time to rework it. I just hope I did it right. True? I know I've been there. Just say, time is up, I got to turn it in. So at any rate, we flip the rectangular pulse around, and what I always, and I think I mentioned this last week, but I'll just mention it again because it's kind of a universal thing about problems. Whenever you have say x, and you're going to consider it as x of x of n minus k, you want to get a sense of where it's going to show up on the axis. So really what you're doing is you have an understanding that there's something that changes when n goes from, say, less than 0 to greater than 0, or whatever the situation might be. So I just simply say, I write the argument out. The argument of x of n minus k is n minus k, and then you just start studying it to say, when is that going to be, say, less than 0 for the particular situation at hand. And then you can just say, in terms of k, when k is greater than n, right? It's just as simple as that. I mean, I'm not applying it to the specific picture here, but I'm just saying it can be that sort of terminology there. You can just see you have to plug something in, put something in the right hand, put the change of variable in there, n minus k, and then solve for the action. What values of k on the k-axis will result in the argument being less than 0. And that's, in this particular case, though, it does explain, what's happening out over here when k is greater than n. That flipped rectangle is turned off at that point. And you could use it to get the other edge if you wanted to, too. Generally, if you're doing something like this, you do have to figure out two different edges so you know what the leading edge and the trailing edge is. But once you get, say, I always forget my microphone lets me walk around, that if you know this is here and you know it started n samples in the past, you can just look at it and say, because it was flipped over, this has got to be to the left-hand side because this was the pulse ending and this was the pulse starting. So you can kind of deduce that it's going to be n minus something to know that it's shifted further to the left. I'm not burning you up on this, but you do have to think, and once you get rethinking on this stuff, it'll start to make sense. But I do like emphasizing it because this is the beginning of any problem where you have to, say, set it up. And if you make your mistake at the very beginning, it's pretty much trash the rest of the way through. And I'll have to wade my way through it to figure out, what happened because of that. So in this case, though, when we do that flipping, we see when n is less than 0, we don't have any overlap, so that's condition. The first condition where we get no output while n is less than 0. Then the next condition is when n is greater than 0. And by looking at the waveform, it has to be as long as this part is not engaging. So we have to condition ourselves by saying n is greater than or equal to 0, but then also to make sure that n minus a quantity capital N minus 1, in other words, this edge right here, is still less than 0. So I would just, plug into that, say n minus the quantity n minus 1 is less than 0, and that's just saying n has to be less than the quantity n minus 1. I mean, that makes it rock solid. That's a condition, because its scenario is going to change as soon as this thing slides one step beyond that. So in this case, we're just summing from 0 to n, because that's the overlap, and we just have to take the product of the two waveforms. One of them is 1, the other one is a to the k, and so that just sets our limits to go from 0 to n. We have a to the k, and without any knowledge, you would say, I've seen that somewhere in calculus, probably, but you may have seen it, you might remember it from 2610, 3205, but I'm going to spend just a few moments doing a classical example, because I had a professor a long time ago that did this back-of-the-envelope calculation about how to prove the geometric series sum formula, and once you've seen that, to me, it kind of enhances your understanding about how it works, and if you forget it, you can just go back and prove it to yourself again. It's not a super complicated problem. So I picked that variable, but I probably should pick a different letter. So I'm going to ignore the summation. I'm just going to write it out. I'm just going to say when k is equal to 0, I have a to the 0, so that's 1a squared, a to the n, right? That's just running it out approximately. And then I'm going to drop down here, and I'm going to say s times a is equal to, and I'm just going to write this all out again, except now I'm going to carry the a through, so I'm going to get a plus a squared plus a cubed plus dot, 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 a to the n plus 1. And then, obviously, this proof has got a trick to it. I mean, any proof, you can't start any problem. Every problem has to be done differently, right? So this particular proof starts off by messing around, basically, with what's the pattern here, what's going on. So what you can do, S stands for sum, by the way. So I'll subtract the second line from the first line. So I'll get S times 1 minus A, doing factoring on the left side. And then on the right-hand side, as soon as I start subtracting, I'm going to lose all those terms because they're going to get annihilated in the subtraction, right? So I'll be left over on the right-hand side with 1, and then because I'm subtracting, I'll have a to the n plus 1. So rearranging, I have that for the finite geometric series. It has a total of n plus 1 terms because it starts at 0 and goes up to n. But there's different ways you can remember it. I just remember it as 1 minus the ratio to the 1 power higher than the upper index, so that's n plus 1. And the denominator has 1 minus the ratio a, and that's the formula. And that's true, right? Because you've seen it in the table I gave you, and you saw it in this problem. But now the cool thing about this is that you can modify this you can make it be the infinite geometric series. So we can take the above answer and say, what is that going to go to? And we can say if magnitude of A is less than 1, then we know that as n goes off to infinity, the a to the n plus 1 term is going to shrink down to 0, right? Because we raise a number that's less than 1 to a higher and higher power, and it's going to be smaller and smaller and smaller. So that's the answer to the infinite geometric series. Now, I'm spending a lot of time on this because the finite geometric series and the infinite geometric series both show up over and over and over again. They're going to be in different locations. We're going to see them in the time domain right here. We see them in the Fourier domain, frequency domain. We'll see it in there as a geometric series. And then we go to the Z domain. We'll see it there again. So it's like for continuous time linear signals and systems, you think about some integrals and calculus stuff with changes of variables and stuff like that. Here, we just need the geometric series sum formula very often. That's all we really need to base our proof on or our analysis on. And then sometimes we end up having to change variables in a sum, whereas in calculus with continuous time stuff, you'd be changing variables in an integral. So changing variables in a sum is actually easier because you don't have to worry about differentials and things like that. All things you learn in calculus, though. But we are lazy by nature. We don't want to do any heavy lifting, in case somebody really kicks us hard and say, you must do this. You want to just try to find your way from the start to the end as quickly as possible. Any questions on this? I'm not taking on the other more complicated series, but this one I think is easy enough that it's kind of cool to see it worked out. And maybe you've seen that before. Any of you ever see that when you were taking calculus? Okay. So you can take the finite geometric series, and generalize it to say starting at n1, ending at n2, and then come up with this formula. We could prove that if we wanted to, and I kind of hinted at that. I'll just say a way of proving this would be to start with k is equaling 0 up to n2, and then you can subtract from that. This was a hint in homework problem number 1. Subtract from it a sum that stops one term below that guy. Right? Does this make sense? I'm going to sum from n1 to n2, and I'll replace that by a sum from 0 to n2, and then I'm going to do a sum from 0 to n1 minus 1. So I'll stop one less than where I start from the series, so I won't include n1 in my subtraction. And then this should be equivalent. Does this make sense? Same idea with holding calculus, right? You could set up a couple integrals and subtract integrals or add them and things like that. So, did anybody use that in their solving of problem number 1? It worked, though. I did it that way, and then I also did it using a symbolic solver, and they both got me the same answer. That's why I gave the hint out, because I had figured out that I would try that approach just for something fun to try, even though the symbolic solver worked beautifully and it worked quickly. And maybe you have a renewed interest in Wolfram Alpha now, I don't know. Nice stuff to be aware of. Okay, for our problem at hand, though, this is what that first case gives us. When we get n greater than 0, we get the finite geometric series, and then when we finally let n be greater than n minus 1, we're now totally engaged with the decaying exponential pulse or sequence, and now our sum limits are set from the left-hand edge of the rectangle pulse up to the right-hand edge at n, and now the sum limits cover this region. We could go back to the general geometric series sum formula and just plug in directly, but I want to encourage you to just say, I can take this on, I can just, I can figure it out. I can figure out how to reindex a sum. So rather than doing the sum subtraction that I was just mentioning right over here, rather than using that this blue box equation, you can just jump right in and say, I think I can get this. And the way that I would get at it, and I used the same variable name after I did the substitution, which was probably kind of bad form. But I said, let's just replace k by a new value of k that's got a shift on it. So what I'm going to do is I'm going to shift this much or subtract this much away from k. That way I'll be sure to make my sum start at 0, and I'm going to have to make sure I sum over the same number of points. So in my upper sum limit, I'm also going to subtract that same amount. So now my sum is covering the same range of values. I've just shifted it back to start at 0, but to make up for the fact that I start at 0, I'm going to have to add that factor in wherever k is I'm going to add on to k inside the argument of my sum that shifted value. And everything is in equilibrium. Is that you should see it as the sum is the same, and I'm going to get the same answer because I'm just patching it up by adding something back in. And that's change of variables in a sum. So now when I do that, of course, this piece in here can pull right out in front because it's not a function of the sum index k. It sits out in front, and now I've got a finite geometric series once again, which I can sum, and now I've got both pieces, and there was the answer. And the homework problem is a little bit different than this, but it has 4 parts to it. It has 2 intervals that are 0 and 2 that are active. So, but it's still kind of similar, because that was a triangle which went down to 0 and ended, whereas here it's an exponential that goes all the way out to infinity. And an important property that I pointed you at last week is in here, this first example of doing convolutions in this little example packet, 2 finite length sequences. This is an important thing to commit to memory. There's actually a homework problem in the book that asks you to prove this, but I've proved it here already. But the thing that you want to keep in mind when you have 2 finite length sequences, and then you can extend this to semi-infinite if you want to, but when you have a sequence x that starts at n1, ends at last non-zero values n2, and h starts at n3, last non-zero values n4, the thing that you commit to memory is this. The output of the convolution is going to start at n1 plus n2. That's the first non-zero value, and that comes down here at the very end. I guess I just say it in words. The first non-zero value occurs when at n is equal to n1 plus n3, and the last non-zero value is at the sum of the 2 last values in each of the sequences, n2 plus n4. It's a good thing to have in memory, I think. And the number of points in the convolution is going to be bounded by, the starting point. I guess I'm in this guy here. I'm in starting point, and the last non-zero point, the largest non-zero point on the axes is n2 plus n4. And then you subtract those 2 numbers, and then you subtract, then you get the answer. Is the number of non-zero points is at most the length of the input sequence plus the length of the output sequence minus 1. And we'll be coming back to this again and again at certain times in the class. We'll be looking at one example of this will be when we're looking at using a fast Fourier transform to implement a convolution using the fast Fourier transform. And if we want to implement a fast convolution using an FFT, we have to understand the linear convolution, which is what we're talking about here, has length nx plus nh minus 1, so that will point us in the right direction for making a fast convolution using the FFT. You don't have to worry about it right now, but we will look at that at some point. One of the tricks that an FFT can do, it can do convolutions exactly. There's no approximation involved in that sense. Okay. I did examples of this in Mathematica because one time in my life I made everybody contemplate using Mathematica. I don't know if it's still available for free for CU students, but it was last time I checked. But Maxima does that. We have Wolfram Alpha, but I got interested in using it for a while. But I'm not going to look at this example. Then I talk about some other examples in here. rather than just looking at it here, this is when I first merging Python stuff into my course notes. I'd rather just look at a quick example over here in Jupyter. So we'll jump down to the Jupyter Notebook. Just to review again, Lantus, we had our discussion on Sunday afternoon. You were not running the starting cell at the top of a notebook. Just think you got to do that. Just like if you're writing C code and compiling code, you have imports or includes, they're called in C. Python needs to have includes as well. MATLAB made you lazy because MATLAB had the includes automatic behind the scenes in its setup. In Python, you have to be a little bit more up-tempo about your programming skills, and you have to include libraries so they're available. But once they're imported, then they're in your workspace, and you can do whatever you want to, because Python is an interpreted language. It's not compiled, so once you have them imported into your namespace, you can get access to them. And I've cheated here. I've imported all of the NumPy, and that's what the asterisk means. It's like a wildcard that you're familiar with. And I've imported all of PyPlot. And then I've just imported abbreviations for Scikit DSP COM/SIG sys module as SS. And I've imported SciPy signal module or package as signal, and signal is useful for our filter function, lfilter. This is a bunch of little helper functions that I wrote. PyPlot is for doing graphics. NumPy is for adding, subtracting, multiplying, dividing, anything with vectors. It gives us all the powerful vector capabilities that MATLAB had built into it. MATLAB was created back in the 80s, I think, early 80s, and MATLAB stands for Matrix Laboratory. So that's what the creators of it intended it to be, and it was actually based on a government program, and then the MathWorks bought rights to it. There was another company that bought rights to it, and then the MathWorks did something or another to, I don't know, they did some stuff behind the scenes to make sure that they had rights and the other company didn't have rights. I think LabVIEW had something. I don't know. It's an interesting story. Companies take government things like Maxima was developed by Department of Energy, I think, for symbolic mathematics, and then the government basically turned it into open source software, and then the people that developed WX Maxima, the Windows and other operating system GUI interface, they just developed something called WX Windows, a windowing C++ library, and they wrote a GUI around this thing that was created by the Department of Energy a long, long time ago, which actually predates Mathematica. I think Mathematica probably leveraged Maxima, or the original software before it was called Maxima. Should you care? I don't know. Everything is based on things going way, way back from Fortran. Python has Fortran modules compiled inside of it. MATLAB does too. And it's things just don't, in our technology base, those of you working in industry on internships know that things just, legacy things are not forgotten. Legacy are legacy. They're there, and we hold on to them. We don't scratch everything back to zero. I think there's MS-DOS probably inside of Windows 11 somewhere or another, and it goes on and on, how technology just builds. Things are discarded as needed. But at any rate, one of the first things that I thought I'd review is when you see text cells in a Jupyter Notebook, you can double-click on it, and you're seeing the code that I wrote in Markdown language behind the scenes. So these are what are called Markdown cells, and we basically have code cells and Markdown cells that we use. Code cells most all the time Markdown for writing text and things. Sometimes in older notebooks I might have some raw cells. I won't go into that right now, but just think we have two different types of cells. And this one is a header, is all I wrote in here, and Markdown language is a simplified HTML, so it just says I can use the # to control the strength of the header. So two # means it's the second level in the heading structure. So it says introduction, and just this brings up the outline that's always available and allows you to zip to a different section of the notebook. But just see what happens if I elevate that. Now you can see introduction is at the highest level in the outline. So I was trying to structure it with a title and then subsections. So turn that off. Then you can close this back out again by doing Shift-Enter, and then it will use MathJax and some other fancy things through HTML to render out the equations, which I'm very practiced at. I started practicing back around 1988 with the LaTeX typesetting language, which is still the standard in the industry. Typest is coming online the past couple of years as trying to take it over, say that maybe it's time for TeX and LaTeX to go away and get replaced by something more modern. I don't know whether they'll succeed or not, but this Jupyter Notebook relies on MathJax, which is an engine that can render math equations using the internet cloud services. So one thing that you might want to do for homework in the future, you might want to put more than one plot together. MATLAB had this capability with subplots. The capability is here today. So here I just generated over an index from 0 to 24. It's always going to be one less than the largest with A range. You can see that if I do Shift-Tab on the function A range. And this is from my library, SS-Step, or D-Step, I mean. It's just a unit step function, and there's a few examples in here. Not really too much is in this. This is the built-in help. The thing we were looking at over here, SIGSYS, Read the Docs has got a lot more in it, but there's always something available. So I just showed you how you could put two plots stacked on top of each other using subplots. So here the top plot is just the step function, and the bottom plot is a ramp that is going to start at 1 when n is equal to 0 and then ramp up. So they're just stacked on top of each other. And if you're wanting to get a relationship between STEM type plots, it's better to stack them rather than have them laying on top of each other, because they get confusing to look at. So that's just a nice feature. The beauty of using Python and the NumPy vectorization is in this function direct, which is a discrete time rectangle, I can create a rectangle that starts at index n, and I can say it's 5 pulses wide, and if I do Shift-Tab on it, it will tell me that the pulse duration is capital N samples. And then down here in my second subplot, I'm just going to use this array n, which is going to get evaluated by direct to create a rectangular sequence. I can just shift the entire array n by 5 samples, and I will shift it to the right by 5 samples. So what is Python doing with NumPy? It's what you would expect if you were using MATLAB. If I have an array that has so many samples in it, and I put a scalar, subtract a scalar from it, it applies that scalar subtraction to every element in the array. And my guess is you say, I expect that, because MATLAB did it that way. So NumPy does it that way too, because NumPy is patterned after thinking that was ingrained with MATLAB over many years. If you're writing this in C, though, that doesn't work. You have to use special classes and things in C++ maybe to have that automatically, but we can get away with it here. So here we're shifted by 5 samples, and here, when I ran it earlier, I've got that happening. 5 samples starting at 0, and then shifted by 5 samples starting there. Since I'm in a really low resolution to keep my laptop happy, these plots are huge. I could use my scroller and make everything smaller, but then it would be harder. Maybe it'd be harder to read. I don't know. Maybe I could make it a little bit smaller. There. Is the code still legible? Okay. But another quick thing that I'll just do is that I'll use the figure command or figure function, and it's got a lot of options available, but I'm going to use fig size. So unless you know this, you wouldn't know whether you could put it in, but I'm going to go fig, hit tab, and it's going to say, there's what I want, fig size, and in parentheses in here I can put in what would be called a tuple, which is a list of numbers with parentheses is a tuple. A list of numbers with square brackets becomes a list. And to make a NumPy array, you have to take that list and convert it to a NumPy array by writing array around it. Those are just different data types. If you were to look in my Learning Python notes that I pointed you at, it takes you through those foundations. We want to use NumPy arrays, though. Don't get excited about lists and doing lots of list operations. It's very primitive. You can't add and subtract scalars because the list, it doesn't have all those neat properties. I had one student many, many years ago that only learned Python and working with lists. His code was very slow, and it was very, it just didn't work. I mean, he missed the whole reason why we use Python with NumPy and all the other SciPy stack stuff. I still think back, how did that disconnect occur? Because he was the only one in the class that did that. Everybody else got on board immediately, and I think he read a book on basic Python, and that was as far as he went, and just thought, I got to do it like this. It was painful. It was a painful existence for him to have to do everything from scratch. You don't want to do that. NumPy has got compiled C code behind it, so it runs very fast. It's been on purpose. But let's suppose we want to make our figure. It'll be width. Let's suppose we want to make it 5 by 2. So now when I put this up above, this is going to be in inches nominally. There, my plot's pretty squashed down. But you get the idea that you could not have such a huge plot. Maybe you want to make it 6 wide. There, that might be nicer, I don't know. It's just available as something that you can do. And another thing that you have to do when you use subplots is you have to use tight layout. If I was to comment that out, the two plots kind of get mashed together. They don't get laid out properly. So tight layout is just who would have thought? I mean, I went to a conference one year and I said, how can I get my subplots to work? And they were doing tight layout. They said, you have to enter tight layout. I said, where was I supposed to learn that? And to them it was like, well, you just know how to you just do that. So I'm telling you tricks that you don't necessarily find written down clearly. You just got to learn from somebody else. So tight layout saves the day. What'll happen is if you don't put a title on this one and have a title only up here that you want to apply to both, it'll squeeze it together. It'll lay it out nicely. So tight layout is kind of the key to getting a nice looking stack up plot. Okay, the last thing we want to do before we move on in the notes is the pulse response that we were looking at over here. If I wanted to create a function to plot this piecewise guy, and I gave you an example list in prepping for the homework, but I'm just going to go through it here as well. We would have to create a function that we could put an array n into, and then we could have it return y evaluated at each n in that array, and we get that by writing a piecewise function in Python. So we have to learn how to write a function. And in Python, a function is a def. Let me get back over here. I'm back way downstream here. I'm just going to get myself set up so I don't get distracted even further. There. I want to come back into there. So when you write a def, it's a definition, but it's a shorthand def. You write your function out, you give the arguments you want it to take. If you wanted any argument to have a predefined value, all you'd have to do is do that, and then when it was compiled here by doing Shift-Enter, it would be defaulting to n is equal to 10. But if you want to force the user to define all three of them, you don't put that in there. You would write with the double quotes, 3 double quotes, and then closing off with 3 double quotes gives you a space to write your what's called the doc string. And this will
Similar to like using the pound key or whatever, like that hashtag symbol to comment out something. Could you also do that for stuff like this?
you can, but the hashtag just comments things out. I mean, I would not put a hashtag in here.
Okay, because like in C, I think that's what we would do or something, is for everything that you wouldn't want compiled.
Oh, yeah, you would comment it. That would be a / or something like that. Yeah, for here, that's true. But this doc string is very important, and I'll show you once I compile it what writing that in there does. I'm not going to force you to do it, but it'll save your butt at some point. It's like it's giving you a little bit of help right there. And usually when I'm writing code where I work, I will drop down below here and I'll put my name and I'll say August 2025 or something. I'll give a date so I know when I wrote it. And I put my name on there so I know that I'm the one that wrote it. And, you know, you're always supposed to give credit where credit is due. So software's that way, definitely. So I set this off, and the way I'm going to do this is n is going to be an array of integers that I want to span over. A is going to be the parameter, which is in that piecewise equation. N is a parameter that's in the piecewise equation. So n is going to come in as an array of sample values. And for each index in that array n, I want to evaluate the function piecewise from its definition. So it's good form in Python not to be growing a list bigger and bigger. It's good form to make an empty array that you can put things into. That would be what you would do if you're writing in C, right? You have to define your array that's going to hold your variables. So I'll just use zeros. That's very convenient. And I'll use length to say I want it to be the same length as n, and that's going to track, right? Put in an element, an array of so many values in n, and y is going to be the same length, and it will produce its output that way. And then the big thing in Python is how am I going to fill that array? I can't do it vectorially. I have to do it with a calculation. So I'm going to use a for loop. And a for loop is a little bit different in Python than it is in C or in MATLAB. It grows on you, though, and you eventually don't even think about it. So I do for, and I could just do it as for k in, it's always going to be in something. So the notation is more like you're speaking to somebody. It's like for k in a range of values, for k in this enumerated list, which I'm going to explain to you next. It's not, that word in just means like it's in this interval. It's going to lie in that interval. We're going to sweep over that interval in that last argument. I didn't choose that. That's the language. The guy that invented it used in, and I think other languages use in too, maybe Java. I don't remember anymore. I haven't programmed in Java for a long time. Julia uses the word in though as well. So you would just say range length of n, and you could sweep over that value. But a cooler, more efficient way that has nice aspects, I don't always use it because Python is now fast without just using range, using just range. But when I first learned it, it was suggested to use enumerate, and what enumerate's going to do, it's going to take whatever you throw into it, and it's going to say, okay, it's a bunch of values in a NumPy array, but it could be an Python list as well. It says it's going to go analyze it, and it's going to say, it's going to give me, as I step across all the values in this list that I'm enumerating, it's going to give me the index at that particular point when I'm doing my for loop, and it's also going to return the value held at that index. So it's like n contains a bunch of integers, but they could be 5 to 10, 200 to 200,000. I mean, it's not just integers 0 through 5 or something. So I get the index itself, which I use to extract a value, and then I get the value held at that index. And that's useful in the calculation that follows here. So what I have to do in my math is I have to implement, I'm not going to go back there, we have to implement for n less than 0, we put in 0. For n between this interval, we put in something else, and so on, exactly what's shown in here. So we say if nk, the value held at that index k, is less than 0, I'm just going to keep that 0 in yk. Even though I made it 0 up here, I'm being redundant at this point. I really wouldn't have to do any work, but I'm just doing it for clarity. And then I will say else if nk, and this is elif actually, it's a shorthand for else if. Again, Python developer created it, so elif is less than or equal to n minus 1. That's the next condition. Then I'm going to plug in this equation that came from the analytical solution. 2 asterisk is raising to a power. That's different from MATLAB and a lot of other languages. You have to use star star to get a power. And then else, when we finally are ready to bail out, we'll just put in the other evaluation that we have as the else condition. And we always end these conditions with a colon. It will kind of light up at you in a funky way if you don't put in a colon. It's like you missed your colon, you're going to get an error when you try to build this. Now, the hardest thing about doing this, the code makes sense to you, but Python does everything in a structure of a for loop or an if, else. It does everything with indents. And if you've never had any other experience coding Python, you're going to get very frustrated with indents. Why do I have to indent? Well, Python lets you be lazy. If you indent, you know that in the next line when you outdent, you're done. You don't have to close off your special structure. And now the editors actually make that pretty nice and easy, because as soon as you start writing a definition, put a colon, hit enter, it's going to line you up so many spaces over automatically, 6 spaces, I think. It works off of spaces, so if you mess that up, it will get angry at you and it won't compile properly. Likewise, when I do a for and put a colon in here, it says, oh, your next line is going to have to be indented by 6. And when I do an if, it has to be indented by 6. So what I'm doing is when I leave this first if block, I just simply outdent and type another statement like elif, it knows that I'm done with that if clause, and elif clause when I outdent. And when I get to else, I outdent, and now, let's just see, it's thinking I have something to type in there, but actually I'm done with my else, I'm done with my for, and I back out 2 tabs by hitting backspace, and now I'm good to close it off. This is going to be weird if you've never done this before.
It's just about the K and NK. So the K is the
value of the index. Yeah, it starts at 1. It starts at 0.
It goes 1, 2, 3.
Yeah.
Okay, and then NK is the amplitude.
Is the value held at that index? Yep.
Okay.
Yep. And if you don't.
Where is that initialized? Is that initialized like in this code?
In the for statement, when it enumerates, it picks up what's inside of n, and it's just going to start counting at 0 because that's the way Python works.
The first if right there is just for index value 0?
Less than 0. The if nk, the value held in the array.
Okay.
Yeah. That way this thing works if the indices held in n are shifted out here or shifted way back over here, it just will automatically calculate properly. Indices always start at 0 in the array, but the values held at that index can be anything. So this allows you to have a powerful function that's reusable.
So n is the array. So for k and nk, are those just things you define in the for loop?
Yeah.
Does that make sense? Okay.
Yep, it does.
So is it like the first, so you can name k anything, right? It would still be the index of
Yep.
the array, and the nk is the amplitude or whatever?
Yeah.
Okay.
If you use enumerate. If you didn't want to use enumerate, what you would end up doing, and I'm not going to kind of trash my whole bit of code here, you would then just have to take all of this away, and you would just put in range. You would say for k in range, and range just starts at 0 and goes merrily along. There's options for range too. Range is not like, I'll just put in a blank line up here. If I go over inside of this and go Shift-Tab, it'll tell me range, what I can do with it. I could start at a value other than 0, but I generally started at 0. And then you could end, or you could put in a step. And another thing about range, and I want to show you this too, because he'll say, if range inside of a for loop is actually going to index, why can't I just put range outside and get an array of indices? Watch what happens. It says, it doesn't do anything actually. It just tells you that it's a range starting at 0 and going up to 5, but it doesn't actually let you do a calculation. It only can be used inside of a for loop. And it's supposedly optimized for speed, so it doesn't have anything else to slow it down, and when it's used inside, and it knows, Python knows that. When I first started coding in Python, you had range and a range was used like what we're using right now outside of a for loop, and range was inside, but then there was some other option. I don't even remember how it worked. It was confusing to me, and then they modified the language in the next iteration, and then range became only good inside for loops, and it's supposed to be really fast. So most of the time when I'm in a hurry and I don't want to think, I might just not even use enumerate. I might just simply use range. And then what I'd have to do in here is I have to change my code slightly. I don't have nk, so I have to actually go n at k as I move along in here. I have to change things around a little bit. I'd end up not using nk. Instead, I'd have to replace it with n at k, because I didn't have nk already. I'd have to just sort of create it on the fly. So this keeps you from having to do that step with the enumerate. It's supposed to be faster, and we'll time code later using a function called timeIt, and we'll see if it makes any difference or not. Okay, so now I can compile it, and if there was a typo in here, you would have seen it immediately. It would have gotten kind of ticked off, like suppose I did that. It gives you an error message like, on indent does not match any outer indentation level. I created a word, I guess, when I said outdent. I don't think that's a word, right? It's fair, though, isn't it?
Yeah.
So, pardon me, on indent, I'd use Shift-Tab. So, or I just use the backspace. The editor is already set up to kind of lead you down the path of not getting hacked up. When I first started coding, I would have to use Tab and Shift-Tab. I would have to bring everything over to the far left and then just start tabbing in. And I would have to set the editor up to go 6 spaces. But now in a Python editor, they just automatically have it pre-configured like that. They tried to make it easier because people complain. People that write in C or another language, they say, what I really don't like about Python is, and then the other people will say, what I really don't like about C is, right? Everybody's picking, everybody is not happy. They want something exactly what they want, and they write about it. But I think people get over this sore spot pretty easily. But if there's anything to complain about, this would be it. So now we can just create an array n running from -2 to 25 because I'm adding 1 onto it, and now I'll just use our function. But now if I go Shift-Tab inside of there, notice what it did for us. It created a doc string, and then we can get instant help on it. We can see whatever we put in there to help us remember how to use it. It's now available. So it's kind of like teaching you to be a better coder.
That's cool.
So it's pretty nice. And if you're lazy, you don't do it, right? And then you get a pile of code that you have to remember what it does. And if you share it with somebody, they won't appreciate it, probably. But what is AI doing? You know, you can turn AI on in VS Code if you use it. Copilot is what Microsoft calls it. It tries to second guess and tries to analyze your code and tries to start writing your code for you. But how well does it work? Or how well do you think it works based on what the media keeps telling us about AI?
It's so great.
It does everything, right? You're not going to have to use your brain ever again.
And when you actually go use it, it's like complete trash, and you're like, fuck this thing.
Well, it does. Some things it does really well, but other things it's like, no, you don't know what I'm talking about. Get out of my way. I got to write this out. You're not helping me. But other times it works. For me, it works beautifully. If I'm repeating a structure and it's a pattern that's being repeated, it will hit it almost perfect. But if I'm doing something very creative that I'm using my brain to do, it doesn't have my brain. It has its own thought process, and it's not good enough. Right now, I don't feel particularly threatened by it. What I do, though, is I feel worried that we're going to have things that are going to do bad things and kill people, or just be kind of scary. So I don't know what you think, because you've been indoctrinated more. I wasn't teaching when it was so popular. Now it kind of scares me a little bit that we have a bunch of bad things going on, a bunch of cars crashing because the traffic lights are, just doing bad things. We're not using our brain anymore. We'll see where it's going to go, though. I'm sure it will get better, but you got to have added value, and you're the added value person as an engineer, right? I don't think you can take your added value away. Otherwise, it's like taking your very being away and saying you don't need to exist, and that's not. I don't know. That's definitely not good. Okay, so here I just plotted a bunch of variations. I reuse the function if it runs for me. There it is. So I just put in some different parameters, and then I use another thing, label. If it's added to stem, you can put a string of characters in there that show up in a legend. Only thing you have to do to get the legend to work is you have to write just a legend command underneath. So pretty nice, I think, if you're exploring something. And then the last thing we'll do here is just the direct convolution, that we could take any pair of sequences and just directly convolve them. So we'll take 0.6 to the nx and then start it with a step function at 0, and then create our rectangular pulse with d step, or we could have used direct if we wanted to in one function, but create h over here, and then I'll use the convolution sum. So bring that up immediately with the shift tab, and we just have to, the way I wrote this function is I wanted to make sure that convolving two functions just gives you a function, but it doesn't tell you what is on the x-axis. It doesn't tell you where it starts and where it ends. So I give it the extra information of saying what is the support interval on the x-axis for the first sequence, that's nx1. What's the so-called support interval on the x2 waveform, which is nx2. So that way, when it brings that in, it can give an array to plot the returned convolution at. And it returns ny and y both, so that way when we go ahead and plot it, we get the right axes down below here. SciPy.signal does have a convolution function. So if we didn't have the function that I created, we'd go into signal.co. We got a bunch of things with CO. We have convolve in 2 dimensions, we have correlate in 2 dimensions. We will eventually get into correlate in this class. It's the opposite of convolution. Rather than flipping and sliding and correlate, you just slide. And correlate is like holding a transparency up to itself, another one, and sliding it around until it correlates and gets a strong alignment. I mean, we do that a lot, I think. In thinking, we think, is this correlated with that? So we'll learn about correlation later. But convolve is the one we would use. And then once we're into that, we can go shift tab on it, and we can see it doesn't take in an array like that. It just takes in 2 inputs and does it. So does that help, Miles, with your question earlier?
Yeah.
Okay. I wish I had more time, but then I'd be exhausted because I'd be talking forever. But there's a lot of stuff to learn, right? And I'm fanatical about details, and most engineers are. I'm sensing a little bit about personalities, and I'll know more as I grade papers. What extremes of detail level you're thinking at, and that's what older people always told me is, the details is what matters, and that's what you get paid for, being very focused on details. So, okay, so we're about at the end of this first session. I guess this is a good stopping point, even though you just closed the door. Yeah, it is getting annoying for me. Is this a good time to take a break?
Yeah.
Some of you have already taken your breaks, but let's do it. Let's come back at, 6:04, 6:15 would be good if we can do that.
Where do I turn in the homework at?
Slack.
Direct messaging.
Just direct message you?
Yeah, direct message it to me. I think you just drag and drop it on there in Slack. You might write a little message to me like, here it is, and I'll write a message back saying thank you. And I'll probably get it right over here. I'm going to stop the video, though, for the time being. started the video again. In the future, if you ever see me not do that, yell at me because I'll have a blank video. So we're running again now. So properties of LTI systems, alluded to that last week, didn't really have time to go through it, but these are all pretty fundamental things that you've seen before, but just reviewing things. When you have a linear time invariant system, you have some really, really nice properties. Cascade and parallel connections are two of those, and they take advantage of the convolution property or convolution theorem that we've already established for LTI systems. So we use the impulse response. So we say if we were going to take the output of the H1 system and feed it into an H2 system, we would use the commutative property of algebra and establish that, well, we can say that we're really convolving X with the convolution of H1 and H2. And that makes sense, doesn't it? We can just do that. And then we can use, take that further, and if it's commutative, we can change the order and do things like that, because we know from the beginning there were two different forms for the convolution formula, right? So we're just leveraging that again to say that we can change H1 and H2 around the order of them, or we could have it as one system. Now, these are theoretical ideas, and we know in circuit theory, continuous time signals in systems, we know these properties hold approximately for analog electronics, but cascading is very sensitive matter in an analog circuit where you might overload and overdrive and have an impedance mismatch and all kinds of different things that would go on in electronics. But in an algorithm in the computer, we can get away with this fairly well if we're in floating point. If we're in fixed point arithmetic, then we have to be careful again, and we'll maybe explore that later. But on the computer with Python, we're using double precision floats right now, just like MATLAB does. We're getting away with all kinds of great things. We're getting a concept of our ideas in double precision math, and if you want to explore what happens when it's fixed point or less dynamic range, then you can do that too. Because did I show you the data types that NumPy has? I don't know if I did or not. It's in that Learning Python document about NumPy. It supports all the types that C does. So you've got int16, int32, int64. You've got float 32s, float 64s, float 128s. You've got complexes and all the different sizes. You can constrain Python to use certain types, and by default it uses high precision integers, and it uses doubles for all of its math. Actually, Python does something that's very unique onto the language, and that is it does an infinite precision integer. It goes outside the box of what NumPy does. It does integers that have an infinite number of bits, which is mind-boggling. But I did have an engineering problem that I worked on with a PhD student for a company here in town that makes cameras and imaging systems, and I took advantage of that in modeling a fixed point math problem using the infinite precision of Python. It was actually very handy. I'm not going to get sidetracked on that right now, but it's just like you have tools and you're trying to make tools work for you, and that's what it is, right? And I thought it was interesting that Python had infinite precision integers, and then all of a sudden I thought, I think I can use that, and I used it for something, and it was great. Most of the time when I'm using integers now, I might pick a 64-bit signed integer and do a lot of work just in that size. It's like a package that I can do a lot of modeling in. I'll get into that. So there we have series connection. Parallel connection is putting your boxes side by side, and that, of course, works. So then the impulse response will be the sum of the impulse responses, as opposed to up here where it was the convolution. And these are the pictures that we get used to looking at. for these types of configurations of subsystems. So now we're going to jump to this theorem, which I talked about before class, which was important in the homework, and hopefully you were able to use it. I will feel embarrassed if you did not use it. I hope that my hints were good enough. Does anybody remember getting pointed at this theorem?
Yeah.
I'm pretty sure I put it in the hints. I said use this theorem. This theorem is very powerful. It says, and this is an if and only if theorem too, which means it goes in both directions. Said an LTI system is bounded input, bounded output stable if and only if the sum of the absolute value of the impulse response is less than infinity. So in the forward direction, we look at it as less than infinity will establish that it's bounded output stable. And if we start with the less than infinity, then, and we work in the opposite direction, we can establish the opposite direction. Namely, I probably said that backwards, but one is we're going to leverage the less than infinity, and the other one we're going to conclude stability. So one of the proofs is given down here, and then I have the other proof given further down the page. The first one is probably the one we think of the most, though. If we're bounded input, bounded output stable, we would go to the convolution sum, and we would assume that the input is stable. I mean, the input is bounded, so it's some bx, and then in this convolution sum, we're going to use this right in here, and I'm going to ask you to think back to calculus maybe. Do you remember that something called the triangle inequality? I'm curious whether you had a math professor that brought up the triangle inequality.
Fever dream?
Pardon me?
Fever dream?
A fever dream?
Yeah.
Like at some point.
We probably did learn this, but it's just like hazy.
Oh, okay. Okay. I wasn't sure what you were thinking about fever dream. It's like you had a fever and it burned out of your brain maybe or something, and you lost it. You no longer have it stored. Well, a triangle inequality is just simply this. So that's kind of what's going on in here when we say we take the magnitude. Now we're going to take the sum of the magnitudes, and of course, a sum of product. I mean, a magnitude of a product is the product of the magnitudes, right? So I just sort of applied another property in math with absolute values, and then when you do that, you can, this term pulls out front over here from the bounded input property, and then you're left with this part, and then you have the theorem, the proof at that point. So just give you a flavor of how that works. And then there's a proof by contradiction in here, but I want to keep moving. So what's another nice property that comes out of LTI systems that I'm not really proving, but I'm just stating it right here, that a system is causal, then it follows that the impulse response is 0 for n less than 0. And just to let you know that I'm not totally going to necessarily leave you hanging. If you want to read about it, you can go down to course materials and this LTI and causality. So you can take a look at this picture and get an idea of how that comes into play. Basically, though, I'll just say that if we're doing the convolution this way, and this is our x of k, and this is our h of n minus k, so it's a flipped over impulse response. The future inputs are right here on our input x of k, and if the impulse response has something setting up in here, then those future inputs will be getting used to calculate the output. And in terms of the flipped over signal, this is just one way of looking at it, but the flipped over signal, what that's saying is that the impulse response values, if they're non-zero, this is actually corresponding to n less than 0 in the unflipped and shifted signal. So I realize I just said a lot in a short period of time, but it makes sense if you think about it. But you have to think about it, and I realize we're in the second half. I'm starting to get a little bit delirious, and I'm sure you're getting delirious too. True or not? Your brain just starts to get foggy after a while. That's the downside of doing a long lecture, and I know it's hard. There's more in here too. I'm not going to go spend more time on that, but why do I have all these notes anyway? It's because I taught this class so much. Anytime something came up in class, I said I'm going to take an action item and write some other explanation up. So that's how these things got collected up. So then there's a couple more definitions in here which we'll be playing into shortly, and that is infinite impulse response and finite impulse response. So impulse responses, we know for causality they have to start at n is equal to 0 and go to the right for causal, but we also know that if an impulse response is finite, like when we were convolving in homework problem number 1, it was a rectangle with a triangle, that we get an output that's finite in duration. So the impulse response, though, in that case of the system, or of the waveform, was finite, and that's the term FIR, and we'll have FIR filters later on. And FIR has a nice property that as long as the amplitudes in the impulse response are finite, then the output will be stable. So the third bullet there is infinite impulse response. So like the exponential decaying pulse that we had in that example, that's an infinite impulse response scenario. And we have filters like that too. And we have those in the analog world more commonly, because you think of an RC low-pass filter, that is an infinite impulse response. You put a blip into it and it takes forever to decay to 0. It decays, but it runs out for a long time. So in the discrete time domain, we have the two classes, FIR and IIR. So I did some examples in here, kind of like the homework problems, just showing that a delta is it's stable, and as long as ND is greater than 0, we're also causal. Then I go to an impulse response that's a step function, which we're going to see in a picture here shortly, is known as an accumulator. It's accumulating the present input with all of the past inputs. We talked about that last week, I think, too. The accumulator is not stable, because if we take and plug into our LTI theorem and sum the absolute values of U of n, we get infinity. So if I was you, I might think, well, why is the professor talking about accumulators as being pretty nice? If they're not stable, how can they be useful? Well, think back to analog electronics. The integrator was a pretty nice function in an op-amp, and an integrator was useful in modeling. An integrator is not stable either, if you think back. You put a fixed bias into an integrator, and what does it do? It integrates up to a rail, like in a power supply. Did you ever do that in the lab? Let's say, did you ever have an op-amp where you had an integrator built because you put, say, a capacitor across the terminals, output to input, and then you put a bias in, or just the op-amp all by itself might just integrate up to infinity with a bias offset or bias current or voltage in the op-amp. So analog integrators are very touchy things to work with, but if you wrap more feedback around it, it works. It's stable. The accumulator is stable also for the same reason. So, okay, variation on that is a to the n u of n, which we're going to see here before the class over with tonight. Is that stable? Well, that's our geometric series. If we have an impulse response that's a to the n u of n, it's going to come down to this sum like we were looking at earlier, and that's the geometric series. So it's stable as long as the coefficient A has magnitude less than 1. And we'll see a lot of that happening throughout the rest of the semester too. This is like the RC low-pass filter. This is equivalent to an RC low-pass filter, and I'll sketch that out sometime too, how it is equivalent. So now we're into difference equations, which showed up in the homework a little bit in one problem, but that one problem was easy because I gave you the answer in the types document. I don't know if you found it in there or not, but it was in there actually. I sort of did that intentional and unintentional, but I said it's okay. You have to look around and find stuff. So we're gonna study difference equations though for the rest of the class. So we're gonna start drilling into the difference equation idea. So the basic idea of the difference equation, it's the parallel to the differential equation for an analog circuit. Linear constant coefficient difference equation is what we have, and it just so happens LCCDE is the same acronym for differential equation too. So when I wrote the dummies book, they didn't like me doing that. They wanted me to make it unique because differential and difference are two different animals. So here it's a difference equation. Same idea though as a differential equation, except it's a discrete time version. Powerful in DSP, powerful in digital controls, any signal processing algorithm. But in our lives, it's also in economics. Difference equations show up in banking and in economics. Not that that's what we do, but if you know about difference equations, you can get into economics and modeling there too from this background. And I have one of my former master's students that left an engineering firm and now works in business using his DSP, I think. I'm not positive, but I think he is. So some people have bailed out of DSP and EE and gone into modeling for economic type stuff. They've always existed in the mathematics, though. Difference equations show up in there maybe first, before digital signal processing was popular. So here's the accumulator that we looked at before, and I think I just talked about this last week, that if you form an accumulator is just taking and summing up all the past values of the input up to the present. And then we could rearrange this accumulator by subtracting the accumulator at n and the accumulator at n minus 1, which is now on the right side, and we just end up with the isolated term x of n. And then if you rearrange that difference equation in here to be the output from the past input, or past output, and the present input, we have it like this. So this is what makes the accumulator so useful, is that it's a very simple calculation. You just have to do one. These are the coefficients in the difference equation, and this is the block diagram of what it looks like. We have one adder and we have one delay register. So it's a very simple little thing to implement and wrap other feedbacks around this, and then this works great. So the moving average we talked about last time, I almost feel like I want to skip part of this, but this is an interesting example just the same. Did anybody look at this already and see where I take this example? Because it leads to how you can, it leads to two properties. Number one, in this parallel circuit theory, a different differential equation can implement the same system. Likewise, a difference equation can implement the same system, so they're not unique. And I think in circuit theory, you would have to agree with that. You can do your topology of your circuit. You could use inductors and feedback in a different way that you might use capacitors and things of that sort. So there's, a circuit design is not unique to implement a particular function. You could use a different topology, let's say, and difference equations are the same way. So here, I took the moving average and I represented it as in a different form. So I said the moving average looks like this, and this looks like a feed-forward difference equation where we're taking the present output and we're feeding forward, just like this model up here shows, we're feeding forward the present and past values of the input. We're not using any past values of the output in the standard moving average system. So these are the way the coefficients get defined. And we can get the impulse response of the moving average system by just firing a delta function into the input. And then we can get at that delta function in terms of the difference of two step functions. Now this seems kind of strange that I could do that, but this is saying that what survives out of here is just m2 plus 1 delta functions. Does that make sense? That's all it is. And so I could take a step at n and I could subtract a step delayed off by m2 samples, and then we'll be left with those delta functions in the middle. So that kind of hints at the possibility of taking this implementation differently. And we also notice that a delta function convolved with a step function will just give us the step function shifted by whatever the delta is shifted by, because that's kind of like the property you learned a long time ago that says a delta function is like a replicator function. You convolve anything with a delta function and what you get, that function. And if the delta function happens to be delayed, that delta function just replicates the function delayed, right? It's kind of like a rubber stamp or something is the way I think of it. It just copies it over again, but it'll copy it over with the delay in. So we could, in this system up here with the steps, we could write it as the difference between two deltas convolving with a step, and these deltas would go with these steps and it would create the difference of steps. So we've changed our topology slightly. So what that does is it says our topology now is we have a scale factor, and then we come in and difference through two different paths, one that's straight in, one that's delayed by m2 plus 1 samples, and then we throw an accumulator at the end because that's what this is saying. Remember, the cascade formula says we convolve impulse responses in the cascade. So in terms of what this is, that's one system, and that's the second system in the cascade. Actually, it's three pieces. One's an attenuator, then this is the splitting system. So there's 1, 2, 3. What's the advantage of this over the straight moving average is that the accumulator only has one addition in it, and there's just one addition or subtraction in here. So the math here is simpler than it is to do that sum over large values of m, is what it comes down to. Now the trade-off is you have to have a register that can hold past values of the input, and that register is basically like a shift register in logic. But this is a wide shift register. So a shift register that you saw in logic circuits was just a bit in each element of the register, right? So in an FPGA or in a or VLSI implementation, you can have a shift register that holds lots of bits that all just shift down at the same time. And those bits would hold the least significant bit up to the most significant bit of some representation of a number. And what's your favorite representation? I don't know. 2's complement is what's used most of the time to represent signed numbers. And that's what we would typically use to have a signed number. So it could be a signal. I'm biased. I have to have wide digital words be signed numbers because I like signals flowing through them. If you were a pure logic person, you'd say, I like unsigned better, but I don't like unsigned because I don't get to have negative numbers then. So Okay. The quick little example I have here in the notes is a example from a calculator. This is a nonlinear difference equation that my understanding from where I got this from a long time ago or read about it is this might be an algorithm that a calculator uses for a square root algorithm.
Sorry, going back to the last example, how, I don't really understand how that last block would be the accumulator.
Here?
Yeah,
Okay.
because isn't that just like the,
It's this convolution,
yeah,
and that's the final part of the cascade. We first have the gain. We have the difference between a signal at time n and a signal that's been delayed to m2 plus 1, and then there's a convolution in here. This doesn't have a convolution because it's just a multiply. It's a gain factor. It's not a convolution. So
is accumulators just some function involved with use of them? Or,
the accumulator's impulse response is u of n. If you drive in this function right here, if I drive a delta into this, okay? You're asking a good question because you can visualize it from the picture. If a delta arrives here, like the system's at rest, so we can take our definition of impulse response says system is at rest, and what is an at rest system from this picture? I would say that this is holding nothing. It's empty, right? It's drained out. It doesn't have a value. So a delta fires into here, comes down the path, comes to the output. But that delta comes into here, gets delayed by one sample, comes down in here, comes in, comes around again, comes to the output. Does that over and over, it's caught. It's just going to keep going around and around, which is why it's a non-stable system. But it's useful if feedback's wrapped around it. It can manage this, so that's what it's doing. And that creates an impulse response, which is a step.
so the impulse response of a system, you can use that, what the result of that impulse response of that system involved with other systems?
Yeah, because that's defining this system. It's saying u of n is the impulse response, and that is our system model, and we can convolve it. That's like H2 in that block diagram from earlier, right?
Okay, perfect, yeah.
If you're like me, you're struggling from that lightheaded feeling. I'm so lean that my body burns stuff off fast, and I'm pretty bad shape. When I run out of energy, my body just collapses really fast. So I'm starting to go down really rapidly. You know what I'm talking about? I call it bonking. My wife doesn't like me to use that word, but I think that's the, yeah.
That's cool. I bonk.
Okay. I mean, when I'm riding a bicycle, like when I rode this summer, I was climbing too many hills in a row, and I wasn't taking enough Cliff Bars or energy stuff. People on the ride with me gave me their gels that they had. That was my first time to use gels this summer. You know what I'm talking about, those energy gels?
Yeah.
They work. They worked almost immediately for me. It's like pure sugar or something. One of them I had, the best one I had was honey energy gel. I put that in me, and I was by the road for just a few minutes, and I was able to start producing enough energy to climb hills again. Almost.
Bounce out with protein.
What's that?
Gotta bounce out with protein. Whenever I did my 12-mile runs, I would have my pocket full of Skittles.
Okay.
And peanuts. So as I hit my next mile mark, I'll just eat some Skittles and some peanuts, and I'll just keep running. And 12 miles, 3 hours, 60.
Well, to me, yeah, peanuts are a balance. I used to eat those a lot too. I still eat them actually. So, yeah, when you're doing anything, I'm sure soccer is your example, but when you're riding like this day where you're doing 72 miles, and we had some pretty harsh conditions. I mean, harsh conditions that we were on some roads that were parts of the route that were not super fun to ride on, but and lots of hills, of course, too. But it's scary for me at least, but that helped me out a lot. So people were always offering me energy if I was falling behind or if I was just struggling. And I can usually keep it up if your body is bonking. What can you do? You're dead, right? You got to change your state somehow or another so you can get it back again. And sorry if you don't like my use of that word, but I see it written down that way too. My wife just doesn't like me using it because it has another meaning too. But I don't know how I got sidetracked on that, but being tired, I guess, is the example. So this thing is cute. You can just play with it if you want to. It's a square root algorithm, and it has an initial condition that you put in it, but it's definitely not a linear constant coefficient difference equation, right? You look at that and you say, that doesn't fit, linear combination of inputs, linear combination of past outputs. Okay, so what we're going to study for a little while, and then we're going to move to the Fourier transform, is linear constant coefficient difference equation solving. Most books don't go through this anymore. I got into putting it in my notes because the Oppenheim and Schaefer book does do it. They just don't tell you how to do it. They just give you the problems and they think you can do it without having an explanation. So I dug in deeper into how to solve classical LCCDEs. And this is kind of interesting because all of you took a course in differential equations, right? Do you have fond memories or just so-so memories of it? I didn't hear exactly what you said, but somebody that you had for the class. Okay, well, think about differential equations. The one that EEs like the best are the linear constant coefficient differential equations, right? Because you use the Laplace transform to solve those. And then we use that in circuits, and we love that stuff, right? But there is a classical solution to differential equations and difference equations. So just to spend a little bit of time on that, the classical solution method, it just parallels the continuous time that you had in differential equations. We have a homogeneous solution. We have a particular solution. The homogeneous solution is also known as the natural response. So it's what the system does based on whatever state it might happen to be in without applying an input. It's like there's some charge sitting here or something else. In the case of the difference equation, it's some initial states into the difference equation. So we take we get our homogeneous equation by setting the right-hand side equal to 0, and we just have all of these past values of the output sitting inside of it. And when we get the particular solution, that's the forced response, and that is might bring up something from your past of differential equations. Do you remember the method of undetermined coefficients in solving linear constant coefficient differential equations? I'm just curious. I mean, I have this thick differential equation book. I took differential equations too. I did more of that kind of stuff too. It was fun. I mean, I kind of minored in math because of where I was at in my program, but at any rate, these things hold for discrete time domain too, our difference equation. So we take our forced response and we can then drive it with a particular input x of n, and what we're going to see with the particular solution is we're going to see a remnant, in a sense, of this input shows up in the output because we're forcing it in to our system. So think of continuous time systems where you have sinusoids and things. If you push a sine wave into an electronic circuit that's linear and time invariant, you see a sinusoid coming out, right? If you push a delta in, you might not see the delta, but you'll see some transient coming out. You put a step in, you're going to see a step coming out. The delta is kind of special. The delta might come out. It depends upon the type of difference equation or differential equation, but that's what we're talking about. And in order to do that, just for this little introduction, we have these types of particular solutions that we have for certain types of inputs, and we're mostly interested in probably this one right here, just the constant. These others all hold true. They're very nice. We have the Fourier transform, and in Chapter 3 we have the Z transform. The Z transform actually does all this stuff automatically for us. But I want you to have a little bit of taste of this because I think it builds your body up a little bit. You know, have this understanding to know that this does exist. It's not like you know it exists for differential equations and you outgrew it quickly because you didn't want to stay there, right? None of you like that, I don't think. You're not going to like this a lot either, but I want you to see just a little bit of it to have an appreciation for it. And then I think you'll appreciate the Z transform even more. So you have the characteristic polynomial when we're going to solve the homogeneous equation, and our general solutions are of this form, Z to the n. And the Z is the same variable we use in Chapter 3 of the Z transform, and it has the exact same kind of concept behind it. So here's our homogeneous equation. We set the x's to 0. We can then factor a polynomial out of this in terms of our general equation form, Z to the n, and we get this polynomial, the characteristic polynomial. And we find the roots of that characteristic polynomial, and those are what are the modes of our system. The things that we're oscillating at in our system are defined by that the roots of that characteristic polynomial. And bounce back over to this for a second. If you're sitting here in Python and you need to find roots, you can find that just like that. So you have the roots function available in Python just like you'd have, I don't know what's MATLAB's called again, roots, is that true? I don't remember. It's been such a long time for me, but we have that built into what we do in things like Z-plane and other functions that I wrote for my package. And of course we can factor that in different ways, and that's what's going on here in the notes, right? Exactly. So we have a characteristic polynomial, has roots, real, complex, distinct, repeated, and we have our coefficients. So if the roots are distinct, we get our general homogeneous solution will be composed of all of these different roots that are decaying with the exponent n, and then the coefficients that have to be determined from system initial conditions. This should seem like, oh, I've seen all this before. This is just the discrete time version of what you saw earlier in your career as a student. If we have repeated roots, then we have to do something fancy, because if we have repeated roots for a particular root z1, then we'll have, if it's repeated twice, we'll have to add in an n. And if we have repeated more times, we have to add in more things. And to me, what I'm leaning on for your memory is, you know, if you have two S-domain roots, the first one is just e to the minus at, and then what's the next one above that? If you have another root, what's the next iteration that you do in your solution? T e to the minus at, right? And then t squared e to the minus at. So this makes sense, doesn't it? It's just the same exact idea. So let's just do a really simple equation, and then I want to dial ahead a little bit, because there's a bunch of examples in here, things that are talked about in the notes, but I worked in the homework problems. Most of the homework problems you can use Fourier on if you want to. There's a few instances where it's nice to be able to use this stuff, and I drive pretty heavily on this, and I'll post the hints up pretty soon, and you'll see the hints that I give, where it's going to point to examples in here like this. 210 and 211 are two really critical examples that can be helpful in working these problems, but then the other hints will will help you along in that as well. So let's take our first order difference equation. It's got one feedback term, variable A, and we have an input, and this is going to be our a to the n u of n. So this, we've already seen this written down at least earlier tonight. That happens to be the impulse response of this first order system, a to the n u of n. But how do we solve for the output in this classical solution technique for an arbitrary input without resorting to the convolution? We can just go directly from the difference equation. So really what we're doing is by having LCCDEs, we're moving down a particular pathway of linear systems that have a particular form to them. And why are we doing this when we have all these other things we could play with? We're doing this because when we talk about DSP, fundamentally, building systems revolves around solving this equation and having a nice algorithm that we can fire inputs into. We can store the coefficients, the A's and the B's in our system, and we can just get outputs on the fly at any time. So this particular type of LTI system, one that has a representation in terms of LCCDE, is exactly what we want, and you know, that's exactly what we wanted in analog electronics too, right? You wanted to be able to build a network that you can build with lumped elements, and you can, you know, you can make it work. And that's the same thing here, except here, making it work is an algorithm that runs with coefficients stored on the computer and works with sequences and numbers. So even though I'm getting really tired feeling, I'm trying to keep my act together as much as possible. So we're going to assume a particular type of input here just to work this problem out, because this is like anything. We can have many different types of inputs, and right now, until we get to the Z domain, if we had to stick in the time domain, this is about all we could do. But this is actually an awful lot. It's constants, and then a constant times n to the m, and then sine and cosine. I mean, this is really pretty much what you do in analog circuit design. These are the primitives that you get to have for inputs and outputs, things of this sort. And actually, if this is the input, this should make sense, that if we're firing a cosine into our LTI system that's represented by a difference equation, we're going to get out sine and cosine, because isn't your brain programmed on that from what you've learned so far? In a linear system, you put a cosine in that starts at some point and you get a cosine out, but you might get a sine out because there might be some phase shift going on in there too. Isn't that pretty natural feeling? I mean, I think as electrical engineers, you get to thinking that you just feel like I know that's it, because that's called what in general in life? It starts with I. I'm just thinking, it's really late, I know, but intuition, right? Your intuition takes you a lot of places. It can get you into trouble too, and it does. It can get you killed, actually, I suppose, right? Intuition says that car's not going to move fast enough, I'm going to get in there, and then bam, you get hit and fatality. I'm just kind of thinking really extreme, but in electronics, I mean, I'm testing, always using my intuition to try to see what's going on here, try to figure out what's not coming up, what's not happening. So we'll take our homogeneous equation right here, which is just turning off that input, and we're going to substitute in z to the n for the general form of our homogeneous equation. So what that means is homogeneous equation is y. We plug in z to the n everywhere, z to the n minus 1, coefficient a, and we solve, and the root here is a for this first order equation. So the general form of a homogeneous equation is a1, a to the n. If you're thinking this seems really simple, it is, because it's going back to the beginning of circuit theory. It's now we're in discrete time domain. So this is our e to the minus at from continuous time. It's a to the n with an unknown coefficient a1 in the discrete time. Now we go back to our non-homogeneous equation, and we're forcing it with this input. B times u of n is the general form up here, and it's called k in the problem statement, but the particular solution is going to be at the form b times u of n because we're putting in a constant at the input. I wish I could do that. Someday I'm going to be able to pick things up. My strength is getting there, but it's still painful, and all that plastic doesn't let me grab it either. I guess I'm a robot person, Mr. Robot or whatever. That's what I feel like. At any rate, going down here to this, so we have this. This is our particular solution where b is a scale factor. So right now we're going to have something put together that's going to have a1 that has to be determined and b that has to be determined from our initial conditions. So we go to our non-homogeneous equation and we plug in the general solution. So notice what we're doing is we're going up to the original problem and we're saying we're going to plug in the particular solution in place of y, and then particular solution delayed by 1 in place of y of n minus 1, and then we're going to have our input k. So we plug all of these together, and we want to solve for b, because now we're able to do that. And the basic premise is this is going to be steady state. We want to make this hold true, so we want to evaluate it where none of the terms vanish. And this was the terminology in the book I was reading at the time. Vanish sounds like a mathematician word, right? Does that bring back memories to you? Mathematicians like to use kind of exotic sounding words. Vanish sounds more impressive than disappear or go to zero. Don't be amused by it, though. It's just the way people talk, right? So vanishing or disappearing or going to zero. So all the terms are active as long as n is greater than 1. So we'll have b minus ab equals k, and then we can solve for b. So this tells us what our particular solution is. And it's controlled by the fact that we're starting at n is equal to 0, so we put a u of n at the end. So now our total solution is homogeneous a1 a to the n and particular k over 1 minus a. So how do we solve for a1? Well, we have an initial state in our problem. When we start up this difference equation, unlike the impulse response, which was an at-rest system, this is a system that's starting for n is greater than or equal to 0. So when we start running this thing, we have to have a value for that. If we're at rest, that'll just be 0, but we might have an initial value in any type of application you could kind of envision. You might have an initial state. And in DSP system, states are very important, actually. In analog circuits, they are too, but you have to charge up a capacitor, you have to charge up an inductor with current. In a DSP algorithm, you just have to put a number into it and you've given it, an initial state. So what we have here, we say that C is the initial value held. We're just being symbolic solution right now. So we write out y of 0 is equal to a1 plus k over 1 minus a1. But we can also write out from our original difference equation, we can write out, just going back up to here, we can say y at 0 is equal to a times y at minus 1, which is going to be c, right, plus x at 0. So right down here, we plug that in, and we get, this is going to be our c. So we can solve out of that a1 is going to be equal to, when we put these two equations together, what are we doing? I guess I didn't make that clear. My software doesn't let me draw across a page boundary, but we bring those two together, and what we're doing is we're saying the right-hand side of both of those equations are now set equal to each other. So we have A1 plus K over 1 minus A1 is equal to A1 times y of minus 1, which is C, plus K, and that's what I'm putting together right here, and that's what allows you to solve for A1. So you can solve out of that A1 is equal to this. So that's our undetermined coefficient. And now we have our general solution to the difference equation that takes into account the driving function, amplitude K, takes into account the coefficient of the difference equation itself, which is like an RC time constant, if you want to think of it that way, and then the initial value in our algorithm. If we have what's called the zero state response, which means we're at rest, then we just have this. This is kind of like what we had from that example problem, except now we're driving our input with a step as opposed to a rectangular pulse, but it's kind of similar to that. So if we wanted to recursively solve the difference equation, we could just rearrange it so we solve for the output in terms of past inputs and in terms of present and past, or past outputs, I mean, in terms of present and past inputs. And we could apply our auxiliary or initial conditions, y of minus 1 through y of minus n. In this case, we're just first order, so we can do this recursively. We can just take our difference equation and we can say y at 0 calculates out to a times c from the difference equation plus k, and then we can bootstrap that up to y at 1 and the pattern that you get out of this at the end is you're able to see that that's just a geometric series, right? Finite geometric series. So now we have the general solution for our first order difference equation by the classical technique. So I don't know if this is cool. You'd probably say I'd rather use the Z transform. We'll see that in the next chapter. We'll probably rather use the Fourier transform, but it's kind of nice to know that you can do this. So this is an interesting property. If you take into account non-zero initial conditions, what this tells us is the response of the LCCDE is not in general linear because we have this output floating around because of a non-zero initial condition. And it's not going to be time invariant because if you try to move the input along the time axis with the parameter n0, that tracks fine with this, but this term, again, because of the non-zero initial condition, does not track with time because it eventually disappears. But the author of the book brings this up because it just wants you to emphasize the fact that if we have zero initial conditions, we are linear all the way through. We don't have any breakdown in the LCCDE. It's just the initial conditions that, strictly speaking, violate that. But I think in circuit theory, we've come to accept the fact that we do have transients that die out in a system if we're driving it with something. So it's still called the linear constant coefficient differential equation, and it definitely holds true if we have zero initial conditions or initially at rest. So that's this last bullet right here. Okay, a second example that's in here, which I'm not going to go through, but I'll let you go through because I want to jump ahead to frequency response and Fourier transform for the last 10 minutes. This just is a second order system, so it has two roots from its characteristic polynomial, and this is an example that shows up in the book. It's not a very practical system because the roots of this system are magnitudes are greater than or equal to 1, so this is a non-stable system. And I have it worked out down here in the Python, I think. I have this problem in here, and then I do some plotting of it. I don't think I cranked it out, but if you go through it, you see that, oh, this example, I guess, is stable. This is another example that's in the notes. But at any rate, I said I'm going to talk about Fourier transforms, so I'm going to be on this. This is also in the section where we learn about how L-filter lets you crank difference equations by just calling L-filter. So you're really solving the difference equation. You're not solving the classical solution, but you're actually implementing what was being implemented right here. Where did I write that out? This is really what L-filter implements. It says, I'm going to get you the output if you give me the input, and you can put in initial conditions. If you assume they're 0, then this term doesn't exist. It goes away. But actually, it doesn't go away. You have to, you want to say that. But it all comes true for, you started off, and if the initial conditions are 0, you just have zeros pumped into here until you get to n is equal to 0 and beyond. So that's what L-filter allows us to do. And if we actually go down here far enough, I've gone back to taking the a to the n u of n impulse response that we were playing around with or introduced a while back. And if you wanted to drive it with a rectangular pulse, which is what I'm doing here, and if you want to take the difference equation equivalent to this, in other words, this is the difference equation, x y of n equals a times y of n minus 1 plus x of n. So if you rewrite the difference equation to put all of the outputs on the left-hand side, we have y of n plus or minus a times y of n minus 1. So those are those two coefficients, the a0 and the a1. And then here, that's the coefficient on x of n. So these are the coefficients that come from the difference equation model and go right into L-filter. And then you can push your input in, which here is a rectangular pulse, and you look at that and you say, I've seen that before. That was exactly what that convolution example worked out. Remember, we had a rectangle and we were convolving an exponential. Sound good? I mean, you're seeing how things are kind of interrelated and how we have different ways of viewing things. Here's a second order example where I put some ringing in it. Then another example I put in here is where we can put initial conditions in. Python allows you to put initial conditions into L-filter if you want to. I'll explain more of that later. What I want to do now for 5 minutes left, frequency domain representation. So this is the next half of the chapter. The first half is time domain. Now we're going to be in the frequency domain for discrete time systems. So how do we get started? We get started by saying we want to see what happens when we drive a system with an exponential that starts at minus infinity. And you might remember Fourier transform, the continuous time does the same thing. When you sit in the lab with a function generator and you have an analog circuit on a breadboard and you hook up the oscilloscope, you see a sine wave coming out, let's say, on the generator, on the scope, and you're putting in a generator. You don't really think about the transients. You think that that sine wave has been there for a long, long time. And mathematically speaking, we just handle that by saying it started at minus infinity. Is that fair? Minus infinity is relative, but from a time constant perspective, we just have to have it run for a long enough time so we don't have to actually think the beginning of time. It's just the mathematical convenience of saying it's in steady state. So that's the way we come up with a frequency domain representation. We say we have a complex sinusoid starting at minus infinity. We pass it through a system with impulse response h of k, and this is the convolution then, and that's what this is right here. We're convolving this is x of n minus k. So we're convolving h with x, and we get our output. And because the input starts at minus infinity, the output is in steady state, guaranteed, because we're starting it all the way back at minus infinity. So what we find out is this eigenfunction property of an LTI system. We see that a function that goes in is e to the j omega n, and the same function comes out. What's happening, though, is that a complex weight has been applied as resulting going through the system. And that's eigenfunction, and in matrix theory we call it eigenvalues, but the eigen thing comes from a German word, and does anybody remember? Because I don't remember. I don't speak German, but it comes from German. It means like principal value. It means the system is transparent. It replicates it from the input to the output. So what we're left over with, though, is how this complex weight relates to the properties of the system, and it comes about through forming this sum, h of k, the impulse response of the system, multiplied by e to the minus j omega k. That comes out just naturally from driving it with a complex sinusoid, thinking of convolution, and then defining that to be the frequency response of the system. Now, what I'm going to run out of time on tonight, but what I want to say without zooming fast, way ahead, I want to say that is the Fourier transform. We're actually taking the Fourier transform and the impulse response to get the frequency response. If we replaced h of k by x of k, that would be producing the spectrum of a signal, whereas the Fourier transform of an impulse response is the frequency response. So it's the same mathematical operation. It's taking a Fourier transform. Is that familiar from past, like 3205 probably? And it has real part and imaginary part. It has magnitude and phase. And due to the fact we have linear systems, if we form a linear combination of complex sinusoids, drive them into the system, we will get a linear combination of those same complex sinusoids coming out, just with the individual complex weights applied based on the frequency of the sinusoid that's applied. Seem okay? My throat's getting kind of dry. Does that seem pretty good? Remember, in the formula sheet, we do have a table of Fourier transform pairs. We have theorems. We have all that stuff that goes on for the Fourier transform. Simple example, if it's a delay, it's just a phase shift. What I want to do, and here's one nice property, though, that we know holds from continuous time systems. We've seen it defined for a complex sinusoid, but if the input is a real sinusoid, then we can use superposition to apply, through Euler's identity, the breakdown of the real cosine wave into two complex sinusoids, pass them through individually. We're going to use a symmetry property, which says that if you conjugate the Fourier transform, for a real system, it's the same as e to the minus j omega. So if you put that together, then you can just say that if you put in a sinusoid at frequency phi, it's going to pick up at the output the magnitude response of the system and the phase shift of the system. Is that not something that you got drilled in your head a lot already? I mean, to me, I always come back to that sitting the first time in my life in the lab with a function generator and a scope and a breadboard. Everybody's done that, right? Sometime? Doesn't that just, it's burned in your brain? Agreed? I mean, and it holds true in any system you're modeling. I mean, if you can model it as linear, you'll have that kind of behavior. So there's a lot more properties in here. I'll let you simmer on it a bit, and then in a couple of days I'll probably post the hints page out so you can start forging ahead if you want to on your own. You will be using the theorem, and we have, you know, a few more pages down where you have the Fourier transform and the inverse Fourier transform. So maybe sad to say this integral, this is the only integral that's in the class. It's in the inverse Fourier transform. Nothing more than that. So we have tables for that. Otherwise, when we go forward, we're going to use the geometric series in here. What we're going to do is we're going to be able to work that into a geometric series. And I probably have an example a little bit down here where I do that, do something with that. Maybe I don't have it right away. Maybe I do. I don't remember where I have it in here, but it comes into play pretty quickly, where you're going to be Fourier transforming an e to the minus, an a to the n times e to the minus j omega, so you just drop that in there, and then it'll be a geometric series again. You'll just keep replaying geometric series. So I like it. I like DSP because I don't have to remember as much stuff. I think I'll stop there. You're tired. I'm tired. My wife was making a new dinner tonight, so I get to not have leftovers. I get to have a fresh meal I'm excited about, not knowing what it is. First, I have to call her to get her over here to get me.
Pasta?